Let me take an aside real quick to talk about notation. So far, we've been using this very explicit notation to write our problem formulation. And what I show here is the Banner Chemicals formulation that we've developed, and hopefully you're comfortable with this. You see the objective function, the 3 constraints, and then the non-negativity constraints. So we talked about this, showed it graphically, and hopefully you have a good feel for what this is doing. However, this is not how we represent models in practice or in the literature. And the reason why is because this takes up a lot of space. And so if we have a problem, typical in practice, I might have hundreds to thousands of variables and hundreds of thousands of constraints. They get massive. So writing them out explicitly like this, it's good to learn, but it's not how you're going to see it for other models, how they get represented. What we do instead is we show a compact formulation. And let me just show you what that looks like. And I want to talk you through it because a lot of times the first time a student sees this, they get nervous. They don't understand what all the Greek letters mean. Let me just talk you through it line by line because these are equivalent notations. So here's the objective function, and that maps directly to the objective function I have in the compact notation. So what it's saying is I want to maximize this z, which is the profit, and it's a function of the different x's. And what we're saying here by this Greek capital letter sigma, it's a summation sign. I'm summing all of the variables with a subscript I that are in the set M. What does that mean? Well, the products are i's, and my M is the total number of products I have. So in this case, my M is equal to 2. I have 2 products, the high and the supreme. And what we do for notation, we just number them now. So this would be 1, and this would be 2. So this is the same thing as saying I'm summing up P1 times X1 plus P2 times X2. Well, that's the same thing as saying 80 times XH plus 200 times XS. It's the exact same thing. It just says it in a much more concise and compact manner. I do this because I could represent 1,000 products in my objective function with this exact same formulation. I wouldn't have to write anything more. In this explicit formulation that we've been using, I would have to write each one out, and it really doesn't give me any more information. So you read this as maximize z is the summation of pi's xi. Okay, so that's the objective function. Now let's talk about the constraints. This first constraint is the capacity at the plant, and that maps directly to the first one in the compact notation. It's saying summation for all i's of x sub I has to be less than or equal to c, where c is the plant capacity. So this is simply saying x1 plus x2 less than or equal to c, which is exactly what we have in the explicit notation. Now the next one is a little more tricky. You just have to get used to it. So we're taking these 2 constraints, the additive constraints, and we're actually making them 1 because it's the same constraint. It's just you're doing it for multiple additives. So I'm introducing another indice. I've got I for each product, I1 and I2, or excuse me, X1 and X2, and now I'm introducing J's for the additives. I have additive 1 and 2. We were calling them additive A and B before. So when I say Aij, what that means is that's the amount, the quantity of additive J required per barrel of product I. So if I have A11, that's the number of gallons of additive A I'm putting into the high grade, and that would be equal to 3. If I look for A12, that's product 1, the second additive, that would be 1. A21, that's for the amount of additive I'm adding into product 2 for additive 1, that would be equal to the number 2. And A22 is simply this. So all we're doing is capturing the essence of the model. So what this constraint is saying, sum for all the i's, right, for all the products, the product of the amount that you have to combine times the amount that I'm creating. This has to be less than or equal to the additive I have available for additive j. So I'm going to have as many of these constraints as I have j's. How many j's do I have? 2, right? For additive A and B. So n is actually equal to 2. Now these signs over on the right, you might not have seen these before. This little upside down triangle looking thing says for all. And then this little sign here is a membership sign. So the way you say this is sum for all the i's, aij times xi has to be less than a sub j for all the j's in n. So it's saying for all the additives that I have. Okay, and then the last one, very similarly, these are the non-negativity constraints. And we're simply saying xi has to be greater than or equal to 0 for all of the i's that are in M. So it seems confusing at first, and it might seem like, why are we doing this? Why don't we just keep with that more explicit one? Trust me, you'll get used to this, and it's so much more powerful. And you'll see, if you read up on this stuff, you'll only see it in this compact notation. No one writes these large models in this very explicit manner except to learn. And it gets even more compact. Let me just clean this up a little bit. Let me just clean it. Because in fact, for a lot of these models, what you're going to, as you do this more, you'll see that a lot of the models get very similar. They have similar structures. So in fact, there's even more of a notation, more compact notation. You'll see it sometimes like this, where it's saying maximize z, it's some function of x, and it's subject to this function of gx, which are all the constraints, and they're less than this b array, which is my right-hand sides of my constraint. It's very compact, and you only use this when you want to just give a really rough idea of what your model is. As you go forward, you will live in this space. You have to become very comfortable with summations and subscripts and understand how they work. We'll only use this notation to get started. This is the on-ramp, but this is what we're going to be doing going forward.